All right, good morning, everyone. It's nice to be back on campus. So, got a quick reminder of what we finished talking about yesterday, and that's Kirschkoff's loop rules. So again, Kirschkoff's loop rules are actually valid for any type of circuit. Doesn't matter if I have one battery or 26 batteries, it'll always work. The difference is, if you're trying to do parallel in series, those only work for one battery. So if I wanted to apply the parallel in series, those things that we talked about previous to this on yesterday, those only work for a situation where I have one battery. Unlike Kirschkoff's loop rules, which work in any general situation. Now, one thing we can keep in mind, though, is all the things we learned about parallel and series are actually embedded inside of Kirschkoff's loop rules, which means we don't have to worry about adding them in parallel, adding them in series, because it's automatically going to do that using Kirschkoff's loop rules. So that's already embedded inside of the loop rules. Otherwise, we just don't have to worry about it. As long as we follow these rules and we follow the sign conventions, life will be fantastic. Okay? So what are the rules? So the rules is, first of all, that the change of potential going from one point back to the same point in any closed loop within inside of a circuit must be equal to 0. This is just conservation of energy. So again, I'm going to start at one point. I'm going to go around a loop, go back to that particular point at which I started at. By the time I get back to that point, my change of potential has to be equal to 0. Okay? The second one is conservation of charge or conservation of current. Just at any junction, I have to have the same amount of current coming in as I have coming out. I can't have all currents going in or I can't have all currents leaving. Otherwise, my circuit's going to fail. It's not going to work. So I need current coming in and I need current coming out. So it just says that the sum of the currents coming in must be equal to the sum of the currents coming out. So the steps we're going to use, again, I kind of quickly wrote these down yesterday, and we're going to apply these today. The first thing is we're going to choose the loops at which we're going to use. So again, not all the loops are independent. So we have to choose a number of loops, whichever ones that we're going to choose. We're going to then draw the directions of the currents. Now, typically, I'm never going to tell you the directions of the currents, so you have to put that in yourself. There is no wrong answer, not technically. Right? The only thing that's going to happen is if you choose the wrong direction of the currents, you'll just get a negative sign at the end of the day. So that means when you do your math, instead of getting 0.1 amps, you're going to get negative 0.1 amps, and it just means you chose the wrong direction of the current. But does that spoil anything? No. Just means you chose the wrong direction. But the magnitude of the currents will be exactly correct. Okay. Then you're going to choose the direction to go around the loop. That's mostly so you can get your sign conventions correct, because again, most of these depend on the direction of the currents. So again, if I go across the resistor in the same direction of the current, I have to have a potential drop. If I go in the opposite direction, I have to have a potential increase. Then we're just going to apply our two rules. We're going to apply the loop rule then, and then the junction rule, and then finally solve. So just to remind you of our sign conventions, I drew those up as well. These are our sign conventions. So when it comes to resistors, in this case, if the current is going from A to B, if I go across the resistor in the same direction as the current, that manifests itself as a potential drop. So potential drop across the resistor is negative the current times the resistance. If I go in the opposite direction, so in this case, if I go from B to A, I get a potential increase because this point has a lower potential than this point. For the battery, if I go across the battery from the negative terminal to the positive terminal, I have to gain potential. So I gain the amount of potential of that of battery. If I go in the opposite direction, in this case, I have to lose potential. Because again, this is a higher potential than this one, so I have to have a low potential drop if I go in the opposite direction. Capacitors, we won't see these until next week, but here, again, if I go across the capacitor in the direction from the positive to the negative, that's a potential drop. If I go from the negative to the positive, that's a potential increase. So these are our sign conventions. So all we have to do is keep these sign conventions in mind, draw out our system, follow these steps, and life will be fantastic. So all we're going to do is get used to writing these things down. So I'm not going to put any numbers for now. The only thing we're going to do is analyze these circuits, come up with our equations, move to another circuit, and then eventually we'll solve one fully with numbers. Okay? So mostly all we're going to do is figure out how do we actually do these things. So how do we apply all these things with our sign conventions? So let's say this is the circuit I want to analyze. So again, I have a battery E1 here, resistor R1, battery E2, resistor R2, R3, and then R4. And let's say the only thing we want to know is what are the currents. So first things first is just to note, first of all, how many currents do I actually have? So anything that's connected in series has to have the same current, which means if I go from this node to this node, if I go down around through this loop through here, all of this is connected in series, which means all of this portion has to have current. All of that has the same current. If I start up at this node and go to this node, if I go along this line that connects all these things together here, everything here is in series, so all of this has to have the same current as well. That's a different current. If I go instead of this direction, stretch a little bit, everything up through here is also connected in series, which means all of that has the same current as well. Which means in this circuit, there are 3 currents. There's one current through the bottom leg, one current through the middle leg, and one current through the top leg. So ultimately, I have 3 currents. How many loops do I have? Well, we saw an example of this yesterday. We actually have 3 loops, right? We have the big loop, we have the top small loop, and we have the bottom small loop. So we have technically 3 loops. Now, as we talked about yesterday, not all of them are independent. In this case, only 2 of them are independent because this one is independent, this one is independent, and the big one is dependent on the fact of the 2 small ones. So the big one is a linear combination of the 2 small ones. Now, from here, step number 1 is I have to choose which one of these 3 loops am I going to use. I'm going to use 2 of them. I just have to choose which ones. So I could either choose the big loop and a small loop, for example, the top loop, the big loop or the bottom loop, or the top loop and the bottom loop. Any 2 doesn't matter. I just have to decide which ones am I going to use. So having said that, which 2 do you want to use? Molly, give me one. Which one do you want to use? The top one. Great. So we're going to call that loop number 1. I'm doing a different color. 1. Nathaniel, which one do you want to use? So we got the top one, so we need 1 more. You want to use the big one or the bottom one? The bottom one. Great. So these are my 2 loops. That's step number 1. Step number 1 is we're going to use this loop and this loop. Good. Step number 2, we're going to draw the directions of our currents. Again, the direction doesn't matter, but typically we can guess the direction based off the direction of the batteries. So again, what we said was that a battery forces current, which we pretend is positive charges, coming out through the positive terminal, going around, in this case, in the loop. So in this case, since my battery is pointing in this direction, it kind of makes sense that the current should be flowing in this direction, okay? So here, we could say, for example, current I1 is flowing through this portion of the loop in this direction. Do I have to say that? No. I could choose it in the other direction. It doesn't matter. But for now, we just want to be consistent, and let's just say it chooses this way. What about in the middle leg? So Clayton, what direction do you want to go in the middle leg? To the left, in this direction. Good. So here, he's saying the battery pushes it to the left, so we're going to choose this guy to go to the left. Now, in the top leg, there is no battery. So there's nothing to naturally push it in some particular direction. It's just going to be depending on how these currents are going into it. Now, for the top leg then, the only thing that's important is, does it satisfy the junction rule? So what's happening here is I have current I1 leaving this junction. I have current coming I2 into the junction. So I have 1 coming in and 1 coming out. Which means in the top portion of the leg, it doesn't matter which direction I choose. Because no matter which direction I choose will automatically satisfy my junction rule. Because I already have 1 coming in, I have 1 going out. So I have stuff coming in and I have stuff coming out. As long as I have stuff coming in and stuff coming out, it doesn't matter the direction which I choose it. So in this case, it doesn't matter. But Dylan, tell me a direction for the top one. What direction do you want to go? Right or left? Right? Right. Okay, good. So we're going to say it's going to go right through R4. So here is my 3rd current. Let's call that I3. Good, that's step number 2. Step number 3 is we're going to choose a direction to go around the loops. So what do I mean by that? We're going to start at a point. We're going to go around the loop in a particular direction. So for example, here in the bottom loop, what you notice is that the current is naturally going in a counterclockwise direction. So the thing that makes the most amount of sense then is for us to also go around this loop in a counterclockwise direction in the same direction as the current, because every time we then go across a resistor, it has to manifest itself as a potential drop. I don't have to worry about any potential increases in this case. So here I'm just going to say I'm going to go around this loop in this direction. a counterclockwise direction. Richie, what direction should we go around the top loop? Clockwise. Makes sense, right? Because again, all the currents are going in the clockwise direction. So in this case, let's choose this guy to go in a clockwise direction, to go in the same direction as the currents. Now this won't always be possible because Dylan could have chose the other direction instead. Instead of Dylan saying it going to the right, it could have went to the left. In that case, they're both going to the left, which means we're going to go opposite the direction of one of them. So sometimes they won't be able to possibly be able to set up your currents going in the same direction, or at least in the same direction as all the currents. It just may happen that way. Good, so that's step number 3. Step number 4, apply the loop rule. Good, so what does that mean? So what that means is we're gonna start off for loop 1, we're gonna start at some point. And then we're simply gonna go around the loop in the direction we said we're gonna go in the loop, and then write down using our sign rules, everything we come across, okay? Now what I usually do is I usually start off as a junction, which means I'm either gonna start off at this junction here or this junction here, so that way by the time I come back, I know I made it back to the starting point because I'm at the same junction I was before. Just makes sense, right? So here I'm gonna call this point over here junction A, this point's junction B, and let's start off at junction A, just for funsies. So how does this work? So basically all I'm gonna do is I'm gonna start off at junction A, I'm gonna go through my loop in the clockwise direction because that's the direction we said we're gonna go, and I'm simply going to write down my sign conventions every time I get to an electrical component, okay? So I'm gonna start here, I'm gonna go up, the first thing I run into is R4. I'm going across R4 in this direction, which is exactly the same direction as the current, which means that manifests itself as a potential drop. So using my sign rules, I'm gonna write that simply as minus I3 R4. That's it. Now I'm going to keep going. The next thing I run into is R3. R3, again, I'm going across the resistor in the same direction as the current, because the current's going this way. I'm also going this way. So again, that is a negative because it's a potential drop. So then I get minus I3 R3. Okay? Now I'm saying in the middle loop, so by the time I get to junction B, I'm going to go in this direction. So I'm going to go across the resistor here in the same direction as I2. So that's also a negative. So then I get minus I2 R2. Finally, I'm going to go across the battery from the negative terminal to the positive terminal. That is a positive increase. So then I get a plus E2. And now finally, I'm back at the junction A. So by the time I get back to junction A, I'm simply going to write 0. That's it. Okay? Nice and easy. Junction or loop 2. So loop 2, we're going to do the same thing. I'm going to start off at exactly the same point, but in this case, now we're going to go around in the counterclockwise direction. So now we're going to go this way. So I'm going to start off here. First thing I'm going to do is run through R1. R1 has current I1 running through it. I'm going in the same direction as the current. So is that a positive or a negative? Negative. I1 R1. Next thing I run into is the battery. I'm going to go across the battery from the negative terminal to the positive terminal. So that is a positive increase. So I get plus E1. Now I'm going to run up through here, get back to the junction. I'm going to cut through the center. So in this case, I'm going to go in the same direction as the current. So I get an I2 R2 with a negative sign. I2 R2. Finally, I'm going to go across the battery from the negative terminal to the positive terminal. So that is a positive increase. So I get a plus E2. Finally, I come back to the junction. So at the junction, I get equals to 0. Okay? Step number 5, apply then the junction rule. So here I have 2 junctions. I have one junction here and I have one junction here. But again, as we talked about yesterday, these 2 things are redundant. Meaning, on this side, this one is telling me that I1 and I3 are leaving the junction while I2 is coming in. But on this side, I3 and I1 are coming in while I2 are leaving. The same thing. I just have to choose one of them. What's your favorite junction? Joe, what's your favorite junction? A or B? A. Great. So A then says, here, I have the sum of the currents coming in. I only have one current coming in. That's I2. So I2 then must be equal to the sum of the currents coming out, but the currents coming out are I1 and I3. I1 plus I3. That's it. Step number 6, solve. We're going to ignore that part for now, is we just want to write these things down. This is how we use these 6 steps. This is how we use the sine rules. Okay? So again, step number 1, choose which loops we're going to use. Step number 2, draw all the currents. Step number 3, choose the direction of loops we're going to go around. Step number 4, apply the loop rules. Step number 5, apply the junction rule. So notice how many equations do we have? We have 3 equations. We have 2 coming from the loop rules. We have 1 coming from the junction rule. How many unknown quantities do we have? 3. We don't know current I1. We don't know current I2. We don't know current I3. Mathematically, how many equations do we need to solve for 3 unknowns? 3 equations. So we have our 3 equations. We have our 3 unknowns. Life is easy. Okay. Let's do another example. So let's say now I have this circuit. I just increased by 1 battery and took away 1 resistor. So now instead of 4 resistors, I have 3. And instead of having 2 batteries, I now have 3 batteries. So here we have the same situation as before. We have 3 loops. We have the big loop, we have the top loop, we have the bottom loop. Again, step number 1 is we just have to choose which loops we like. So Vanya, I'm coming to you now. Which loop do you want to use now? Give me one. The big loop. Right. So now we're going to use the big one. So let's call that loop 1. Good. And Isaac, what other loop do you want to use?
Use the bottom.
The bottom one. Great. So let's use that as loop 2. Good. So now we have to start choosing some directions of currents. Michael, I'll pick on you now. So what direction do you want to take the currents in the bottom portion of the loop? So the bottom one. Go left. Right. So let's call that I1. So in this case, we're going to choose I1 to go this way. Good. Corey, did I pick on you yet? No? Good. Give me a current in the middle leg. What direction do you want it to go?
To the left.
To the left. Okay. So now we got I2 going this way. Good. Zach, give me the one in the top leg. What direction do you want it to go? Good. But in this case, Zach actually was put in a pickle because he had no other choice than to make it go to the right. Okay. Because he has to satisfy the junction rule. So here, if I have I1 coming in, I2 coming in, well, I'm kind of screwed if I choose I3 going in as well. I have to choose it to the right. So Zach actually didn't get much of a choice. Sorry about that. It happens. Everyone's okay? Good. So now that's what? Steps 1 and 2. Step number 3. So now we have to choose what direction we want to go around the loops. Right? So Matt, what direction do you want to go around the top loop? So the big loop. You want to go in the clockwise direction or the counterclockwise direction? Clockwise. Good. So now we're going to go in the clockwise direction for this guy. And Isaac, what direction do you want to go around 2?
Me, Isaac?
Yes, you, Isaac. Isaac, yes.
This is the big one, correct?
No, we already did the big one, so we got the small one. The bottom one. Yeah. So there's no natural way to go in the same direction as the currents, right? Because here, this current's going this way, this current's also going this way. So I'm going to go opposite to the direction of one of them. So counterclockwise sounds right. Okay. Sounds good. We're going to go in a counterclockwise direction. Again, are there correct answers to these? Technically, no. I can do whatever the hell I want. I am the master. Do whatever I want. Now, again, the only thing that's going to happen at the end of the day is I may find out that I2 was negative and I3 is also negative, meaning the direction of those that I chose are in the opposite directions. So what? Doesn't change anything. Okay? Good. So now, step number 5, let's apply the loop rule. So good. So let's name these guys again. I'm going to call this guy A and this guy B. So here we're going to apply the loop rule to the big loop. So where do you want to start? You want to start off at junction A, junction B, or some other place? Doesn't matter where you want to start. Jake, where do you want to start? Start at B. Good. Okay. So in this case, we're going to go in the clockwise direction. So first thing I'm going to do is I'm going to come down through here. I'm going to go across the battery. I'm going to go from the negative terminal to the positive terminal. If I go from the negative to the positive, is that positive or negative? Positive. Good. So I get a positive E1. Good. It was okay? Now I pass the battery. I'm going to keep going in this direction. Now I'm going to pass through the resistor, which has current R1. I1 is going through R1, but here I'm going in the same direction as the current. So if I go in the same direction as the current, is that a positive or negative? Negative, good. So I get a minus I1 R1. My first one didn't really look like a one, it looked like something else. Good, so now I'm gonna keep going. I'm gonna pass this junction. Next thing I'm gonna run into is too high, the battery up here. But in this case, I'm going from the positive terminal to the negative terminal. So if I go from the positive terminal to the negative terminal, is that a positive increase in potential or a negative drop in potential? Negative, good. So now I get a minus E3. Finally, I'm going to go through the resistor here. I'm going to go in the same direction as the current. So if I go in the same direction as the current, is that positive or negative? Negative. So now I get a negative I3 R3, and now I'm back to the junction B. So all that has to equal 0. Is okay? Let's do loop 2. So loop 2, we're now going to go in a counterclockwise direction. So Kaylin, where do you want to start now? Do you want to start off at A or B? Doesn't matter. I don't have to do the same point as I did with Jake. A. We're going to start off at A. Good. So I'm going to start here. I'm going to come down in this direction because I'm going in the counterclockwise direction. I'm going to go to R1, but I'm going opposite to the direction of the current. So if I go in the opposite direction of the current, is that a positive or negative? Positive. So now I get a positive I1 R1. Now we're going to go across the battery, but we go from the positive side to the negative side. So if I go from the positive to the negative, is that positive or negative? Negative. So I get a minus E1. Now I'm going to come up to B. From B, I'm going to cut through the center. Here I'm going to go across R2, which has current I2 going through it, in the same direction as the current. So if I go in the same direction as the current, is that positive or negative? Negative. So now I get a minus I2 R2. Then I'm going to go across the battery from the negative to the positive. If I go from negative to positive, is that positive or negative? Positive. Plus E2 is equal to 0. Good. It was okay? Not too bad. Finally, those are our 2 loops. We're going to apply the junction rule. So now, for the junction rule, I just have to choose a junction. So, Cole, which junction do you like better, A or B? B, good. So at B, according to our picture, I have what? I3 coming in, and the other 2 are going out. So here I'm going to have my sum of my currents going in, which is only I3. Must be equal to the sum of the currents going out, but I have I1 and I2 coming out. So I have to have equals I1 plus I2. Step number 5. Finally, step number 6, solve this mess. But again, we'll save that for a little bit. Everybody's okay? Kind of see how all this works? Let's do one more. A little bit nastier. So now I have 3 batteries, 5 resistors, and much more legs. I just want to do something a little bit nastier so we can see how all this still works. So the first thing is, how many loops do I actually have? Well, I have the big loop, so that's 1. I have this loop here, which is 2. I have this loop here, which is 3. I have this loop here, which is 4. I also have this loop here, which is 5. I have this loop here, which is 6. So I got a whole bunch of loops. Okay. But again, not all of them are independent. So the next thing we want to know is how many currents do I have? So let's think about how many currents I have. Almost. Not quite. You're off by a couple. So let's count. How many currents do I have? Well, again, I have a node here and I have a node here. So anything connected from this node to this node must be in series. So all this is a current. Everything connected from here to here is also a current. Everything connected from here to here is a current. Everything connected from here to here is a current. But also I have a node here and a node here. So this is a separate current. And a node here and a node here. So this is also a separate current. So I actually have 6 currents. Okay. I have 1 current here, 2, 3, 4, 5, 6. Okay. This thing has 6 currents. Which means, how many equations do I need? 6. This is ugly, which is why we're not doing this on the exam. Okay. So, good. Let's talk about this. How many junctions do I have? 4. I have 4 junctions. I have 1 here, 1 here, that's 2. 1 here and 1 here, that's 3 and 4. Again, the number of junctions I have are not independent. Some of them are going to give me redundant information. So here, what we're going to do is we're actually going to use 3 of these junctions. So we're going to apply the junction rule 3 times, which means then we only need 3 loops to get the other remaining 6 equations. Okay with this? So let's write down our junctions. So I have a junction here, A, junction here, B, junction here, C, and a junction here, D. What's up, Derek? Well, not quite, because here, if I call this I1 and this I2, so here I have what? I1, I2, and this current say I3. But on this one, I have I3, I4, and I5. So they're not exactly the same because they're dealing with different currents. Does that make sense? You'll see in a second. We'll write it down. But anyways, as we mentioned last time, we have n minus 1 number of independent junctions, which means if I have 4 junctions, 3 of them are independent. So in this case, I'm actually going to apply the junction rule 3 times and then use 3 loops. There we go. 3 loops to give me a total of 6 equations. All right? Because I have 6 currents, I need 6 equations. So if we use 3 junctions, then we have to use 3 loops. Okay? Now, having said that, step number 1 is, once we figure all that out, which 3 loops do we want to use? Again, doesn't matter, we just have to kind of be consistent. So, Elijah, give me a loop that you want to use. The left one, so this one. So let's call that one, loop number 1. Good. Derek, give me another loop. So what's up? The whole thing, okay. Sounds good. And let's see, whoever. Okay, I guess I'm back up here. Nathaniel, give me the last loop you want to use.
Let's do
The middle one?
I guess.
Okay, sounds good. We'll make it up. We'll see what happens. Good. So these are our 3 loops. Good. So the next thing is we have to draw all of our currents. So again, we have 6 currents. So let's have some fun. So let's say in this portion of the leg, the left portion of the leg, what direction you want the current to go? So Grant, what direction? All right. So you want it to go this way? Yeah. Okay. So opposite the direction of the battery? Well, other way, actually. Okay. So in the direction of the battery. Yeah. There we go.
To say like the current going through R2 is going this way, is what I meant. But
oh, gotcha. For R2. Okay.
Yeah.
So we'll just say in the clockwise direction. That'll make a little more sense. Okay. Who's up? Dylan, give me a current then in this portion here. So the left middle portion. Up. Good. Okay. So I2 is going to go this way. Good. Okay. So now what? So let's skip I3 for now and let's talk about I5. So let's talk about the current in this portion. What direction do you want the current to go in the right portion. So Michael, what direction you want the current to go here? You want to go in the direction of the battery or opposite direction of the battery? Down. Okay, so in the direction of the battery. So let's call that I5. Good. Okay, so what else we have? So let's talk about this portion where R4 is. Let's call this current I4. So Molly, do you want the current to be going upward or downward here? Upward? It's all great. I was trying to give you peer pressure there. So okay. So good. So now we only have this current here and this current here. So going from A to B, Richie, do you want the current to go from A to B or from B to A? A to B. Okay. So let's call that I3. And then finally, this portion, we also need another current. So we either need to go from C to D or D to C. So Joe, what direction do you want to go? C to D. Good. So let's call that I6. Good. All right. Still good. So let's now analyze loop 1. So loop 1, well, first we need a direction on loop 1. Sorry. So loop 1, what direction do you want it to go? You want to go clockwise or counterclockwise? Fine. Clockwise. Okay, so let's draw that blue. So here we're going to go clockwise. Loop 2 is the big one. So Clayton, what direction do you want to go with the big one? You want to go clockwise or counterclockwise? Clockwise. In this way. Good. And then Corey, what direction do you want to go around loop 3? Clockwise. A whole bunch of clockwise is good. So there's clockwise as well. Good. So let's start analyzing. So here we're going to go clockwise. So we're going to go in this direction. We're going to start off at a particular point. Doesn't matter which one we start off at, but Isaac, what point do you want to start off at? You want to start off at junction A or junction C? Yeah, we're talking about just this loop here. Start off at C at the bottom. All right. Sounds good. So at C, first thing we're going to do is we're going to go in the clockwise direction. So we're going to go this way. We're going to go through this resistor in the same direction as the current. So is that positive or negative? Negative. So I get a minus I1R1. I'm going to go across the battery from negative to positive. So is that positive or negative? Positive, E1. I'm going to go through R2 in the same direction as the current. So that's another minus I1R2. Now I'm going to hit junction A. I'm going to go down through the center. So here I'm going to go from the positive to the negative. So if I go from positive to negative, is that positive or negative? Negative. So I get a minus E2. Finally, I'm going to go through here in the opposite direction of the current. So is that positive or negative? Positive I2R3 is equal to 0. Okay, that's my first loop. Second loop. Other Isaac. Isaac, wait, where do you want to start for the big thing? You want to start by A or B or C or D or in the corner, or where do you want to start?
Start at B.
B, good. So here, again, we're going in a clockwise direction. So from B, I'm going to first go through the battery from the negative to the positive. So that is a positive, E3. I'm going to go through R5 in the same direction as the current. So that's then going to give me a positive or negative? Negative. From here, nothing, nothing, nothing. So finally I'm going to come to R1. I'm going to go through R1 in the same direction as the current. So that is also a negative. I'm going to minus I1 R1. We're then going to go across this battery E1 from the negative to the positive. So that is a positive E1. Finally, I'm going to go through R2 in the same direction as the current. So is that positive or negative? Negative. Minus I1 R2, and I'm coming back to B, so now I'm at 0. Finally, loop number 3. So remember, loop number 3 is just this portion here, and we're going in the clockwise direction. So who's next? Zach, where do you want to start? A, B, C, or D? D, good. So we're going to start here, and we're going to go in this direction. So here there's nothing. I'm going to go up through this leg. I'm going to run into this resistor going in the same direction as the current. So I'm going to get a minus I2R3. I'm going to go across the battery from the negative to the positive. So that is a positive E2. Come up through here, there's nothing. Now I'm going to come in this direction through R4, but I'm going opposite the direction of the current. So if I go opposite the direction of the current, is that positive or negative? Positive. I4, R4 is equal to 0. These are my 3 loops. Step number 5, we're now going to apply the junctions. So now we need to know, again, we have 4 junctions. We're going to use 3 of them. Which 3 do you want to use? Want to use A, B, C, B, C, D, C, D, A, whatever other combination you can think of. Which one do you want to use? Where was I? Matthew, Matt, which 3 do you want to use? A, B, C, great. So let's first look at A, and then we'll look at B, and finally we'll do C. At A, we have what? I1 coming in, I2 coming in, and I3 leaving. So this says that I1 plus I2 must then be equal to I3. At B, we have I3 coming in, we have I4 coming in, and we have I5 leaving. So at B, we have what? I3 plus I4 must then be equal to I5. Okay. Finally, at C, we have what? At C, good. We have I2 leaving, I1 leaving, and I6 leaving, which we can't do. So we actually have to point I6 in the opposite direction. We weren't careful there. So let's choose I6 this way. Good. So from here, we can then say that's what? I6, which is coming in, must then be equal to I1 plus I2. Did we mess up the junction rule any other place? I think we're okay. Okay. That was a lot. Everything's okay? So these are our 3 loops. These are then our 3 junctions. From there, that gives us 6 equations. From our 6 equations, we then solve for whatever it is that we want, which in this case are 6 currents. So now we have a series of 6 equations with 6 unknowns we have to solve. It's doable. Take a little while, but it's doable. Okay? So this is Kirschkoff's loop rules. All you have to do is follow the steps, follow the sign conventions. As long as you do those things, no bad will happen to you until you get to algebra. It's the only bad place that things are going to happen. Okay? We'll talk about how to bypass that too. So let's do an actual example. Let's find numbers, and I'll tell you guys how to actually do the linear algebra that we care about. So this is the circuit we finally want to analyze. So this says that we have EMF number 1, which has 80 volts, which is this one. EMF number 2, which is this one, has 45 volts. R1, which is, or little r, which is this guy, this is the internal resistor, has 1 ohm worth of resistance. R1, which is this guy, has 40 ohms. R2 is also an internal resistance, so this has 1 ohm. R3, which is this one, is 30 ohms, and then R4 is 20 ohms. Here we want to determine all of the currents within inside of our system. So let me redraw all this. So from here I have what? E1 connected to R, connected to R4, connected to E2, connected to R2, which is the same thing as little r, connected to what's this, R1, is that right? Connected here to then R3. Did I get all those right? Let me double check. Yeah, R3, R1, R2, R4. All right, so here we know little r is equal to 1 ohm. We know R3 was equal to what, 30 ohms? R1 was equal to 40 ohms. And R4 was equal to 20 ohms. Those right as well? Yeah, 20, 30, and 40. Okay. It was okay? So basically we're going to do exactly the same things. So all we're going to do is, again, we have 3 total loops, only 2 of them are independent. So the first thing we need to do is, again, choose our loops. So Jake, give me a loop that you want to go through. The big thing? The big one? Okay. Is that what you said, or am I making that up? Well, which one did you say? The big one. Okay, good. So big. Good. And Caitlin, what other one do you want to go through? The top one? Okay. So we're going to use those 2 loops. Next step, draw all the currents. Now, just for matching what I did in the problem, so our numbers are going to come out right. So here what I said was I1 was going to the right, I2 is also going to the right, and I3 is going through the center. That's just what I chose. So just to match our numbers, we just want to make sure that's correct. So again, I call this I2, I1, and then I3. But again, on the exam and the homework and all that different stuff, you get to choose whatever it is that you want. Okay. But again, just to make sure our numbers match, I just chose those particular quantities. Okay. Good. So let's look at our junctions. So again, we have a junction here, A, junction B. And the next step is what? To choose the direction around the loops that you want to go. So where am I? Elijah, which direction you want to go around loop 1? Clockwise. Good. So here we're going to go in a clockwise direction. Good. And Derek, which direction you want to go around loop 2? So that top one. Also clockwise. Good. All right. So next up, apply our loop rules. So I got to come all the way back. Nathaniel, which junction you want to start off at, A or B? Start off at B. So here we're going to go clockwise. So first thing we're going to do is go in this direction. So I'm going to go opposite the direction of the current through R4. So is that a positive or a negative? So opposite direction of the current, positive. So you get a positive I2 R4. Now we're going to go across the battery from the positive terminal to the negative terminal. So is that positive or negative? Negative. Good job, me. Okay. Okay. Next, we're going to bypass here, come up to here. Now we're going to go in the same direction as I1 across the resistor. So is that a positive or negative? Negative. So I get a minus I1 R3. We're back to the junction, so all that's equal to 0. What's that? Oh, I missed little r? Oh. I just didn't like little r. Plus I2R is equal to 0. There we go. Sorry about that. I just got overly excited when I got into the battery. Sorry about that. Everyone's okay? Loop number 2. So now we're going to go, what, clockwise through loop number 2. So in this case, Grant, you want to go from A, want to start off at A or start off at B? A, good. So at A, we're going to come up through. First thing we're going to run into is this resistor going in the same direction as the current. So is that a positive or a negative? Negative minus I1 R3. Now we're going to come down to junction B, cut through the center. We're going to go from the battery from negative to positive. So is that positive or negative? Positive E2. Now we're going to go across the internal resistor in the same direction as the current. So that is a negative I3R. We're going to go across resistor R1 in the same direction as the current. So that's also a negative. So good, those are our 2 loops. So now we have to apply our junction rule. So Dylan, what's your favorite junction, A or B? B, good. So junction B says that what? We have currents I1 and I2 coming in and I3 leaving. So this says that I1 plus I2 equal to I3. So good. So this is the application of all the physics. At this point, we are done. The rest is now just algebra. However we want to solve this is however your favorite style of solving coupled systems. One method you can do is the typical one, which, for example, you look at this and see I have an I1 and an I2. And this one I have an I1 and an I3. So what? So this one says if I solve for I2 as a function of I1, I can plug that in here. So now all of this is in terms of, I'm sorry, in here. So now this is in terms of I1. Here I can solve for I3 in terms of I1, plug that in here. Now I have one expression which only depends on I1. I can then isolate I1, solve for I1. Once I know what I1 is, I plug it back into those other two expressions to then find I2 and I3. That's one way. Another way to do it is to learn a tad bit of linear algebra. So what we're going to do is I'm going to teach you this kind of quickly. And the nice thing about this is your calculator will do this for you in about a half a second after you learn how to do it. Now, the caveat to this is don't ask me how to do it on your calculator because I've never owned a graphic calculator before in my life. I know it's possible. I've been teaching this for too many years now. So people have learned how to do it. So once I tell you how to do it, then you go online, go onto YouTube. There are plenty of tutorials on there that'll teach you how to do this. Take maybe an hour to learn how to do it. So that way, by the time you get to the exam, you put in a couple buttons, hit like 2 or 3 buttons, and then you're done. You don't have to do 20 minutes worth of algebra. Okay? Now, to do this, we're going to set up what's known as an augmented matrix. Augmented matrix. So what does that mean? So what that means is we're going to set up a matrix based off of the coefficients of the curves. So basically, I'm going to put whatever comes in front of I1 here, whatever comes in front of I2 here, whatever comes in front of I3 here, and then this last augmented row is for the answer. Okay? So what does this mean? So what this means is I'm going to go back to my equations, and basically all I'm going to do is I'm going to rewrite anything that's at a current, I'm going to keep on the left-hand side. Anything that's not a current, I'm going to bring to the right-hand side. So what that means then is I'm going to rewrite this as, so number 1 is minus I1 R, what was that, 4, oh, R3, plus I2 times R plus R4 is then equal to E1. Here's okay? So all I'm doing over here is I'm moving the E1 to the right-hand side. I'm factoring out the I2 from these two. So this is R plus R4, and then I'm keeping that guy the same. Okay? So in the first row of my matrix here, I'm simply going to write out this expression. So under the column, or under the spot where it says R1, I'm going to write a minus I R3. For R2, I'm going to put a R plus R4. There's no I3, so that gets simply a 0, and this is equal to E1. Okay? So all I'm doing is whatever coefficient goes with I1, I put here. Whatever coefficient goes with I2, it goes here. Whatever coefficient goes with I3, which there is no I3, which means that has to be multiplied by 0, equal to that goes in this column. Okay? Let's do the same thing with the second one. The second one then says that's what? So I'm going to bring all the currents to the other side. So here I'm going to get a, go back. So I'm going to get a I1 R3 plus I3 times R plus R1 is equal to E2. Again, an I1 R3 plus I3 times R plus R1 is equal to E2. Okay. So I'm going to do the same thing here. So I'm going to put in an R3 under I1. There is nothing with I2, so that gets a 0. Then I get an R plus R1, and all this is equal to E2. Okay? Finally, the last equation says that I1 plus I2 is equal to I3, so I'm going to rewrite that as I1 plus I2 minus I3 is equal to 0. So here, I1 has a coefficient of 1, I2 has a coefficient of 1, I3 has a coefficient of -1, and this is all equal to 0. So what this is called is an augmented matrix. It's an augmented matrix because it's augmented from a square matrix by this additional row here. Now, what you're going to look up is how to do what's known as RREF, which is what's known as row reduced echelon form. So what is row reduced echelon form? What row reduced echelon form is, it's a step of mathematical steps where essentially all you're going to do is what your calculator is going to do is it's going to turn this matrix into a matrix that looks like this: 1, 0, 0 number, 0, 1, 0 number, 0, 0, 1. And let me put in the numbers from my actual slide. So this would be negative 0.86, 2.58, and finally 1.73. So what your calculator is going to spit out is this matrix. Okay. How do I read this? Well, again, what I know is the first column here is I1, the second column is I2, and the last column is I3, which means that here I have I1 is equal to negative 0.86. I2 is equal to 2.58, and I3 is equal to 1.73. So this is what you want your calculator to do for you. So this is called, again, row reduced echelon form. It's a function that's basically already built into your calculator. You just have to learn how to actually use it. So once it gets to this, you then exactly read off what each one of these different ones are. That's it. So what this means is that current I1 is equal to negative 0.86 amps. I2 is equal to 2.58 amps. And I3 is equal to 1.73 amps. The fact that I1 came out to be negative simply means that, again, if we go back to our picture, I chose I1 in the wrong direction. Instead of it going this direction, it was actually supposed to go this direction. Does that change the magnitude? No. Just tells me I chose the wrong direction. Okay. So the fastest way to do all of this is to, again, set up these augmented matrix. Okay. So again, whatever goes here is the coefficient in I1, whatever's here is coefficient for I2, whatever here is the coefficient for I3. This portion is just the answer portion, which is whatever all these things are equal to. So again, take a little bit of time, watch some YouTube videos, find out how to do row reduced echelon form on your calculators. I know everybody in here has a graphical calculator. Right? No, you don't have one? A little bit of painfulness, that's fine. So that's it. Monday, I'll give you a couple of these to do as a group assignment before we move on to the last part. So the last part of this chapter is what's known as RC circuits. So we're going to start mixing then resistors with capacitors and batteries and all the good stuff together. Talk about how all these things actually work. So, everyone okay? Now I'm going to teach you all of the fundamentals of how to actually do this. But
That way feels so much harder than circuits.
what's that?
That way feels so much harder than circuits, because when I said before, I was talking about the loops.
Oh, gotcha.
So I was like drawing the loops in my head, and I was
Yep.
like, there's three currents, because when you do mesh analysis,
Yep.
it's like that middle loop has like I2 minus I1.
Yeah, that's what I know.
Oh, gotcha.
And I was like sitting there, and I'm like.